So with the whole quickly opening things, just give me a second. Let me set up everything and we get started for today's lecture. I hope you can hear me. Yeah. So didn't usually take slower than usual today. It's taken some time, I know why, but just bear with me for a couple of minutes. And it should get better. I guess. The internet is also not that great today, seems. It's taking some time. Even people have been joining today. It's already the 10th, 11th session. So I think session number 10 or 11 that I have to see for sure. So I think we are in week 10. So we've got 3 more lectures, including today. Okay, so let me start presenting now. Start presenting. Share my screen. Uh, I think I'm sharing everything is okay. Let me check if I'm also it is on, the recording is on, everything is fine. Okay, let's get started then. Today is power cycles. Let's get started. So let's start with a bunch of objective questions. Okay, I think I have to try it now because one copy paste it seems. In a steam power plant, the saturation temperature at the steam extraction pressure is, your options are A, the temperature at which steam is great. There is a notification. No, it's okay. Pressure, this is option one. Then temperature at which steam starts condensing at a given pressure. The temperature at which steam remains dry and unsaturated at the given pressure, and then the temperature at which steam behaves as an ideal gas. Okay, so these are the 4 options. Steam extraction pressure. Okay. I was able, I was reading this question. The question didn't make much sense to me. I even tried to search this in the books. But essentially, it seems like this question is indicating the definition of saturation temperature. It's saying that at a given pressure, uh, the temperature at which the steam starts condensing is the saturation temperature. So, the difficult question because it remains unclear what the question was about. But anyways, okay. In a reheat cycle, there are your options. The pump work input increases and moisture content at turbine exit remains the pump work input remains the same and moisture content at turbine exit decreases, the pump work decreases and moisture content at turbine exit increases. Option fourth is both decreases. So what do we know first of all? Let us draw this now carefully. Let's try to answer it. Let's see and answer it or not. This will be our T. This will be our S. This is the saturation dome. Let's draw the simple recuperated, simple uh, Rankine cycle. This is how it should look. Something on this sort. Now, generally, what does reheating do? Okay, let's draw that. So in reheating, you basically you either put mix. Wait. So let's say it's a open feed water heater. So in that stream will let's say at an intermediate pressure, it will saturate, cool down to some pressure. Sorry, what am I saying? So if it is an open feed water heater case, suppose I'll choose a more contrasting color. So at a intermediate pressure, you will bleed some of the steam. That steam will cool down, and here you will heat the entire liquid water to some high temperature. So this is where you generally want to end your mixing, and then you pump more work. Now, what should happen with the pump work? The pump work is, if I talk about in terms of specific quantity, so pump work is just VDP, integral VDP, right? Integral VDP. And pump work should not depend on as d by rho. So in that case, pump work should not, what do you say? Pump work should remain constant, but your heat input to the system must decrease. So Qn decreases. I think this is what it should happen. So this is one option. First of all, let's see if the other one applies. Moisture content at the turbine exit decreases. Moisture content should also not. Moisture content at the turbine decreases. Turbine exit decreases. Will that happen? Let's try to understand. Because you have bled some of the oh, this is reheat, not regenerate. So this is regen. Whatever I did was for regenerate. What happens for the reheat state? For a reheat, it makes sense. So even for a reheat, this will follow. Largely, it will follow. Reheat moisture content will reduce. Otherwise, it would have, let's say, to actually see how moisture content is reduced, we have to actually draw a much wider kind of saturation dome. So if you simply go like this, or let's say like this, reheating does this thing. So at a constant saturation pressure, your moisture content decreases. But because nothing is changing on the compressor side, pump work remains constant. Okay. For a regenerative cycle, both of them must remain constant. Okay. That is also an important thing. Yeah. Okay. Next question. In a regenerative cycle, turbine work increases. Either both will decrease. So which one option is correct? So let's look at this one. One thing to note here is because condenser, the flow rate in the condenser is reducing because you're bleeding some amount of steam before it expands fully. Q rejection should decrease. So these two options definitely be there. But at the same time, your turbine output is also decreasing. Okay. Why turbine output will decrease? Because again, not the entirety of the flow is getting expanded. So it should be the option, both option decreases. Okay. And this is the correct option. Note. Why? Because you're not, first of all, expanding the entire steam that you had heated, and you're also not cooling it, the entire steam that you had heated in the condenser. Okay. Second law efficiency of a simple, okay, the fourth question is eta second of simple ideal Rankine cycle can be increased by, how can you increase it? Reheating, uh, regeneration, using additional boiler, using additional condenser. Okay, so first of all, let's forget these two options because they don't make sense as much. What are you trying to say? Regeneration, I think reheating. Uh, you also check. So So this question itself is flawed, as I was suspecting. Both reheating and regeneration increases the efficiency. Okay, both of them, just not both of them does that. So reheating and regeneration is are both correct answers. So I'll now recite the question rather than writing. Uh, the exergy destruction in a real Rankine cycle uh, is zero. Okay, maybe I'll have to write only. In a real Rankine cycle, exergy destruction in compressor is zero, comma X destruction turbine is zero. And the other option is okay. Weird question, again, weird question, but the answer is that exergy destruction happens in all legs of the cycle. Compression also, because there will be losses. Uh, it will not be an isentropic process. In turbine also, it will not be an isentropic process. Even in an evaporator and condenser, there will be finite heat transfer, so you will be losing some exergy. You will be losing some exergy. And if suppose that is, let's say, exergy destruction there, let's say, in principle, let's say it happens, let's say, across an infinite, a finitesimally small temperature differential. Even then, pressure drops will like ensure that there is exergy destruction. So viscous losses in all four legs will ensure that all four of them are non-zero. Okay, all legs, there will be exergy destructions in all legs. So the correct answer can be this. Very weird questions. Okay. Okay, so now let's do some numericals. What is this numerical about? Consider a steam power plant that operates on an ideal repeat Rankine cycle. The plant maintains the boiler at 700 kilopascals, the reheat section at 800 kilopascals. So the plant boiler pressure is 7 megapascals. Reheat happens at 800 kilopascals. Condenser is at 10 kilopascals. The mixture quality of the exit of both turbine is uh, 93%. Okay. Determine the temperature at which the inlet of the high pressure and low pressure turbine respectively leaves. So we need to find temperatures. Okay. Uh, this one is 7 megapascal. This one is 0.8. And this one is 10 kilopascals. Okay. Conditions at the exits are known. So if you know the pressures, you also know the conditions here. Now, what else do you want to know? This is the high pressure turbine. This is the low pressure turbine. And the temperatures are also not same. First of all, I have just consider the temperatures are same. But say it's not same, okay? Then and just learn that is an ideal reheat cycle, okay? Let's not consider any pressure drops. The heating processes. Mm, okay. Because it is ideal, even these processes will also be isentropic. So these will be actually indeed straight lines, okay? So I drew them curved or slanted, but they will be ideal, which means that the entropy, uh, these two processes will have the same entropy. Okay, so let's first find out if at so for that it is actually very easy. You need to just consider the property tables. So now I am opening the property tables. I go to the saturated stream table. Corresponding to 10 kilopascals, I'll find SF and SFG. If you do that, this is 0.696,492 plus 0.93 into 7.4996. Now this value comes out to be 0.6492 plus 0.93 times 7.4996 is 7.6238. 7.6238. Now we need to find a temperature in the superheated regime, which is at 0.8 megapascals, and this S value, S equals to S1, let's say. So for that, I'll go to the superheated table corresponding to the pressure of 0.8 megapascals. I'll browse through the different entropy values, see what two entropy, like two rows have values windowing 7.62 value, say 7.62, um, 7.62, right? So that happens to be between 500 and 600, 400 and 600, and very close to 400 because the two values that window it are this. This will be actually you have to now interpolate, and this happens to be corresponding to 400 and 500. So this has to be x minus 400, or let's say 400 plus uh, 7.57, 7.6238 minus 7.5735 divided by 7.8692 minus 7.5735 times 100, because the difference is 500 minus 400. So in that case, my answer should be 7.6238 minus 7.5735 divided by 7.8692 minus 7.5735 into 100. The value is coming around 417 degrees C. Uh, let's do the same thing again to find the other temperature. I'll go to the property tables for the saturated value of 800 kilopascals, 8 megapascals. For that, I will collect SF and SFG. We'll find SF S2. Plus 0.93 4.616. This comes out to be 6.3385. Now again, similarly, we'll browse through the superheat steam for the pressure of 7 megapascals. Okay. Okay. Now, value comes out to be between 350 and 400. Okay, now the two values are you can see somewhere in between, right? Somewhere in between. So close to 375. So all is precisely do it and then solve it. But the answer comes out to be close to 373 and 416. And that's your answer. 417 or 416 is okay. And then 373. That's your another answer. Now the next question asked to us is the thermal efficiency of the system. Um, okay. So now how do you calculate the thermal efficiency of the cycle with just knowing these two quantities? So you know that the amount of heat added to the system, right? Why? You know at least in the reheat, amount of reheat you know, because you know the two temperatures. And then you also know the condenser, compressor inlet temperature also you know. So we can actually calculate this. Okay. Let me take a 5-minute break and come back. Okay. Okay. Coming back, we did this question, right? We did this question. I'll just quickly copy paste the content required for us to solve the next question. So the next question asks is, what is the thermal efficiency of the system? Thermal efficiency of the cycle. So first of all, I didn't talk about the temp. So now, see the temperatures here and here are known. Okay, we know these two temperatures, the inlet turbine inlet temperatures, but turbine outlet temperatures I didn't mention. So let me do that. So that those will be the saturation temperatures of your of uh, the corresponding to the pressure, right? So these two temperatures are these two temperatures will be so one is 10 kilopascals, the other one is uh, 800 kilopascals. So one temperature is 170 degrees C, and the other temperature is 10 kilopascals is 45 degrees C. Now we can imagine that uh, the density of the liquid, so the compressor work, the glue compressor will be VdP, right? So V can be written as 1 by 1000, and dP we know is going to be roughly 7 megapascals, 7,000 kilopascals. So 7 times 10 to the power 6. So this becomes 7 kilowatts per kg. Is that all right? No. 7 kilojoules. 7 kilojoules per kg. Okay. Now the work done by the turbine is needed to be calculated. So you know the enthalpies we would need to calculate now. Now that is required for us to calculate the enthalpy. So let's say some value will come. Then we also need to find Q out. We can find Q out or we can find Q in. I think finding Q out is much easier because wait, finding Q out is easier because that will be 0.93 into HFG at 10 kilopascals. What is that value? Let me first calculate that value. So 10 kilopascals, the HFG is 23. This value is there, and now I'll just find out the 93% of this value. So 2392.1 times 0.93 is 2224. So 2224 kilojoules per kg. Now let me just quickly find out turbine work also. So actually I need to find all four enthalpies also. So let's say this is one. This is one, this is two, this is three, and this is four. So let's find the four enthalpies before doing anything. Now I know H1, I know the temperature, and I'll find out. So H1 is roughly, I'll tell you, just like how for superheated, I'll go to 7 megapascals, and I'll choose a value between 350 and 400 corresponding to that. This is 3178 plus 304843.9 divided by 2 is 310. Roughly this 3110. Now H2 is to be calculated. H3 also I'll find this quickly. I'll find H3. So your H3 will be for 800 kilopascals. Seven 0.7 plus plus 0.16 into 3481 3267 is 303. So 3301. Now let me just find H2 and H4 also. So these will be found in the saturated tables. One is at 800 kilopascals. So at 800 kilopascals, this is 720.87 plus 2047 500.93 is 2625, and your H4 is how much? H4 is similarly we'll find at 10 kilopascals. This will be 191 and plus 0.93 times 239 2.1. This is 246.46. 246. Now just the difference of these two consecutive numbers. Let me do that also. 3,101 minus 110 minus 2,625. Now you add this with 1 minus 241 plus 6 is 1,369. 1,369. This minus 7. This is the network divided by uh, 4 plus 2 4 becomes around 37.99 and 37.9. The correct answer is indeed 37.6. I'm getting 37.99 because I made some approximations and other things. Correct answer is 37.6. Okay, now Shall we do one more question? We shall do two more questions. Okay. Let's see. The closed feed water heater of a regenerative. Write this question for you. The closed feed water heater of a regenerative Rankine cycle is to heat 7,000 kilopascals feed water from 260 degrees C to a saturated liquid. Turbine supplies lead steam at 6 megapascals at AE15C to this unit. The steam is condensed to a saturated liquid before entering the pump. Calculate the amount of lead steam required to heat 1 kg of feed water in this unit. Let's read the question again. There is a regenerative Rankine cycle. To heat a 7 megapascals feed water from 260 degrees C to a saturated liquid. This turbine supplies bleed steam at 6 kilopascals. Okay, so it's a closed. We need to find just m dot. Nothing fancy here. This dot m dot delta H has to be equated. That's it. Now this should be how much? You're heating this 1 kg of this times CP is 480 or 4.2 kilojoules times when you are heating it from 260 to the saturation temperature at 7 megapascal. So let me find. 285. 285.83, and then delta H of this. So whatever the steam is condensed to a saturated liquid before entering the pump. So this is HFG, I think, the closed feed water heater. We know that H. Now this is Hg or Hf at 6 kilopascals. So this should be at 6 kilopascals. Hf is actually 1213.8. 1213.8. And then you have the temperature enthalpy given at this quantity. So that I have to go and find out from our super tables and go for the 6 megapascal table. 6 megapascal, and then temperature is 325. So midway between 300 and 350. So I have to just take an average of 285.6 plus 343.9 divided by 2 is 2964. 2964.75 minus. And so with this, you're going to get 4.2 times 27.83 divided by 2964.75 minus 1213.8. It is roughly coming around 0.066 kgs per second. 0.066 kgs per second. The correct answer is also in this okay, it is 0.08 rather than uh, let me check because I don't think there is much there. Check. The answer is like the correct answer quoted is 0.08. So maybe I know that it is the distance because the distance is not small. think this whatever I've done is okay. Fine. This is fine. So the next question is, a steel power plant it's on a real time still with a net power output of 50 megawatt. Steam enters the turbine at 8 megapascals on 550 C and is cooled in the condenser at 15 kilopascals by using cooling water from a nearby river at a rate of 350 kgs per second. The isentropic efficiency of the pump and turbine are 78% and 82% respectively. Please find thermal efficiency and mass flow rate. Okay. One thing that we know here, which we can quickly calculate, is thermal. We are given the isentropic efficiency of the turbine, right? We're given the isentropic efficiency of the turbine, and we're also given the the inlet conditions, which will allow us to calculate the outlet conditions first of all. So let's do that. So H P out minus H P in is actually 0.82 times of this entire thing, but ideal. Now, this actually gives you, first of all, let's find out what is HT in. Using the property tables, eight megapascals, 550 degrees C, you're looking at a thermal efficiency of 3.5 to 1.8 units. Entropy is 6.88 units. Okay. At 15 megapascals, kilopascals, sorry, I need to interpolate. At 15 megapascals, actually, I'm able to see that this is in the saturated conditions, first of all. So in that case, I need to find X out, but at ideal condition. Okay. Let me calculate it myself. This will be 6.88 minus 0.7549 divided by 7.2522. So 0.844. And corresponding to that, HT out ideal will be 25.94 plus 0.844 times 2372.3, which is triple to 8.16. So what is your HT out actually? Your actual HT out is minus 3521.8 into minus 0.82. So this is this thing. Minus 3521.8 minus 1. Or 2461. So this is 2461. Okay. Now, Q, or let's say Q out, will be HT out minus HF at 15 megapascals, 15 kilopascals, okay, which is 2461 minus 225.94 is 2235. Okay. Now, let's calculate compressor work. W compressor will be 1 divided by 0.78 into times 1000. The dp is 8,000, roughly 8,000. So 8 times 10 to the power 6. This gives you 8 divided by 0.78. So 10 kilojoules per kg. This is your kilojoules per kg. Your net work, W net, is 3521.9 minus 2461 minus 10. So 1050 divided by 1050.8 plus 2235. 2235. The value I'm getting is 31.9%. Roughly 32%. But let me check. Because it's not matching. Let me see that the overall procedure that I have done is in line with the solution or not, and then we'll say if I missed something. But largely, I think it's more or less there. Yeah. So largely, I think it's okay. Whatever we have done is okay. If there was an issue, let's see. Don't think there's an issue. The correspondingly, if I calculate the flow rate, because I know network, I can basically calculate 1050 was the network, and you want to calculate 50 kilowatts, right? 50 megawatts of power. So 50,000 divided by 1050 is 47.61 kgs uh, flow rate. 47.61 kgs. This is how much you will produce. Okay. Okay, so let's close this. We'll meet next time. Thank you for attending.